Remember what an exponential function is. An exponential function is something like 2 to the x or 10 to the x. So that's not to be confused with x to a power like x squared or x to the 10th. Those things involve the power rule. An exponential function is a different kind of function. X is in the exponent, so we haven't seen that yet. If we think about this intuitively, with exponential growth, the more of something there is, the faster it grows. Right? If you have a bunch of bacteria in a petri dish and they're all multiplying, they're going to be growing a lot faster than if you just had 2 bacteria in a petri dish. So something like 2 to the x is a basic exponential function. That's like a doubling function. You have 1, then 2, then 4, then 8, then 16, then 32, right? So the more there is, the faster it grows. And if you say that mathematically, the growth rate is proportional to how much stuff you have, to the size of the population. Growth rate is the same as derivative. So the derivative should intuitively be something times the function itself, right? So since the growth is exponential, the rate of growth is also exponential. So we have to figure that out. Right, the more money you invest, the faster it'll collect interest because it's collecting interest on more stuff. And that goes, so exponential growth includes money or like a population of deer or whatever, or bacteria, or let's say the spread of a virus, anything like that. Okay, so we're just going to show that yes, the derivative of an exponential function is some other exponential function. We'll start with 2 to the x. That's a simple function. Like I said, the doubling function, that's what the graph of it looks like. These things shoot up very fast depending on what the base is. 2 is called the base in this case, the base of the exponential function. There's the definition. The derivative of 2 to the x is the limit as h goes to 0 of 2 to the x plus h minus 2 to the x over h. So we're gonna do this for 2, and then we're just gonna kind of generally figure out what it is no matter what. So we take that 2 to the x plus h and we rewrite it as 2 to the x times 2 to the h. Make sure you agree that that works. Look at it backwards. If you had 2 to the x times 2 to the h, you add the exponents, so we can do the reverse. So once we do that, we see that the numerator, both terms, have a common factor of 2 to the x, so we factor it out. We've got 2 to the x times 2 to the h minus 1 over h, right? That's what you get what's left over. And then that multiple of 2 to the x doesn't involve h. So whatever's happening as the limit as h goes to 0, 2 to the x is unaffected by that, right? It's unaffected by the limit, so we can just bring it outside and then deal with whatever's inside. So finally, this derivative is 2 to the x times the limit as h goes to 0 of 2 to the h minus 1 over h. And we don't have a way of evaluating that inner limit right now, but we can just look at a calculator and see what it is. So notice we can't plug in 0 because 2 to the 0 is 1. So as always, it's 0 over 0. So just go ahead and go on your calculator, and if you just graph the function 2 to the x minus 1 over x, that's what it looks like. And it is indeed a function with a hole at x equals 0, but that hole appears to have a pretty concrete value. And if you just look at a table of values, it's just some decimal, and that decimal is about 0.69. We'll make that better. We'll figure out exactly what that is. But for now, just say that, okay, the derivative of this thing is 2 to the x times this limit. That limit is some finite number, and that finite number appears to be about 6.9. So for now, we have what we expected. The derivative of 2 to the x is 2 to the x times this number. So times this 0.7-ish number. So it's right, the growth of an exponential function is also exponential. It's a little less since this number is less than 1, but the derivative is still growing exponentially. So it's just some number times the original function. And in general, that's it. The derivative of an exponential function is the function itself times some number. We're going to do the same thing with 3 to the x, but I'm going to spare you the details. Exactly the same thing happens. We factor out the 3 to the x, we bring that out front, we get that the derivative is 3 to the x times this limit. The limit of 3 to the h minus 1 over h. Do the same thing, graph 3 to the x minus 1 over x on your calculator. There's a hole at 0, but that hole looks like it just goes through about 1.1 approximately. So same deal, and we could do this all day. The derivative of 3 to the x is about 1.1 times the function itself. We could do it with 4 to the x and 10 to the x and whatever else, but you'd always get the same thing. You'd always get it's just some decimal times the function. Okay, so here's where it gets cool. Look at 2 to the x and 3 to the x. The derivative of 2 to the x is 0.69 times 2 to the x. The derivative of 3 to the x is 1.1 times 3 to the x. The derivative of 4 to the x is some bigger number, 1 point something else times 4 to the x. So if there were a number between 2 and 3 where this limit, we're going to call it a, was exactly 1, we get the feeling there is. Since 1 is between 0.69 and 1.1, there should be some special number between 2 and 3 where that limit was just 1 exactly, which would mean that that derivative, the derivative of a to the x, would be 1 times the function itself, which is literally the function itself. So what we're saying is there's some exponential function that is its own derivative. The derivative is literally just the same function as it is its own derivative. So I would ask you to think of a special number between 2 and 3. Maybe a special irrational number with a name, maybe one that has a couple buttons dedicated to it on your calculator that you've certainly seen before when you studied exponential growth. So if this were true and that magic mystery number existed, then we would have a function that was just its own derivative. And as you've all guessed by now, that magic number is E. E is about 2.71828. It's an irrational constant between 2 and 3. And in algebra class, you probably were told, look, this function, this number is extremely important to exponential growth, and in mathematics in general, this is one of the most important, significant numbers we have. It's hard to really explain why until now. The function e to the x, which is sometimes just referred to as the exponential function or the exponential growth function, is its own derivative. So remember, e is not a variable. E is a number. Think about it like pi. It's just a number that's special enough that it gets its own name. It's harder. Pi is very easy to explain why it's special geometrically because you can just talk about circles. E is a little more mysterious, but now we're getting a sense of what makes it so special. It's the unique number where e to the x is the derivative of e to the x. So hey, that's a really easy one to remember. And you can think about it as E being for exponential or E being for Leonhard Euler, who was a Swiss mathematician who's, depending on who you ask, probably the greatest mathematician of all time. If you ask me, that's true. Okay, so here's a way to define E that might seem a little bit like cheating. If we just define E like E is the unique number for which this limit as h goes to 0 of e to the h minus 1 over h is exactly 1. If we just say, okay, it seems like there's a number between 2 and 3 that works for that. Here it is. Let's just say that's what E is. That way, if we just define it that way, we can just say that, okay, so the derivative of that thing is that limit times the function itself. That limit is 1. It's just the function itself. So just think about what that means. The size of the population at time t is also exactly how fast the population is growing. So at t equals 1, at 1 second, e to the 1 is e. It's also f prime of 1 is also e. So if there's e things in there, it's also growing at a rate of e. So the value of the function is also the value of the function's growth rate. It's gaining as much stuff at a certain time as it has. The slope of the tangent line in the picture is exactly what the value of the function is. So let's play with that a little bit, because that makes it makes some cool things happen with regards to the chain rule. And then e to stuff is one of the most common functions you're going to see in mathematics. We use e to something to model lots of different stuff. We'll get back to like what 2 to the x and 3 to the x is. We'll return to that. We're just going to go off on e for a bit now that we have that it's its own derivative. So e to the negative x would be like what we call exponential decay. So if you think about the derivative of that, okay, the outer function is the exponentiation. E to the something is the outer function by the chain rule. So we deal with that first. What's the derivative of e to the something? E to the something. So it's just itself times the derivative of the inner function now is the exponent. And it's a little, that's not as clear, but that's how the chain rule works, right? The e to the is acting on everything, and then the negative is just acting on the x. So the derivative of negative x is just the constant -1. So the derivative of e to the negative x is negative e to the negative x. So for exponential decay, the growth rate is just negative whatever the value of the function is at a certain time. We see stuff like e to the 2x or e to the 0.1x or something. That's how compound interest works. That's how we model most population growth. If you have e to a constant, so k is just some constant here times x, imagine it's 2, that's okay. The chain rule says the derivative of the outer function, which is itself, times the derivative of the inner function. The derivative of kx is just the constant k. So really that's just a general version of the thing we just did. It's just the constant times the original function. So again, that's not a new rule. It's just something that you'll see happens with these functions when you start applying the chain rule. If you have e to the sine of x, I want you to notice the pattern here. The derivative of that is, okay, the outer thing is just itself, so it's e to the sine of x, times the derivative of the inner function, which is sine, so it's just e to the sine of x times the derivative of the sine, which is cosine of x. So you see the pattern, we see e to a function a lot, and if we want the derivative of that, it's just itself, e to the function times the derivative of whatever that function is. Right, so again, not a new rule, just a generalization of just a pattern we pick up on. If you have e to the g of x, the derivative of that is e to the g of x times g prime. Okay, so now we got to get into the weeds a little bit to figure out what the derivative is of all these other exponential functions, right? E to the x isn't the only exponential function. The base can be any positive constant. You never see a negative base for an exponential. It's not impossible, but it's not applicable. So we're going to do a little, this is going to be a little mathy, but I want to show you why it is what it is. So we have to think back to algebra class. The natural logarithm of x, or ln of x, is a function that was invented to be an inverse of e to the x. So we said, hey, e to the x is a one-to-one function. That means it should have an inverse, but let's call it a logarithm. I don't know where they got that word, but that's just what it's called. I.e. means in other words. In other words, they undo each other. So the natural log of e to the x is x, and e to the natural log of x is x for any number x, no matter what that you stick in there. That's just the definition of what an inverse is. So we're going to use that to figure out the derivative of 2 to the x based on our knowledge that e to the x is its own derivative. So this looks goofy, but you'll have to just come along for this ride with me. We're going to take the number 2 and we're going to rewrite it as e to the natural log of 2. That's just a needlessly complex way to write the number 2. So if we're talking about the derivative of 2 to the x, we're going to rewrite that as the derivative of e to the natural log of 2 to the x. Again, don't ask why. Just bear with me. It works. All right. So we can use exponent laws to rewrite that. If you have a power to a power, you multiply the powers. So that's the same as the derivative of e to the natural log of 2 times x. Now don't get it twisted around. The natural log of 2 is just a constant. It's not a function. It's just some number. It's just some decimal. So this is just e to the kx, where k, our constant, is just this number, the natural log of 2. All right, so we know how to do that. That's itself. The derivative of the outer function is just itself, e to the natural log of 2 times x, and then times the derivative of the inner function. And natural log of 2 is just a constant, so this is just kx, where k is just ln of 2. So that's it. Remember, this is the derivative of 2 to the x. It looks terrible now, but we're going to clean it up. So now we just go in reverse. We say, okay, e to the natural log of 2 times x can be put back like that. If a power to a power, you multiply the powers, then you can undo that and rewrite it back like this, where it's e to the natural log of 2 to the x. And then we go all the way back to the top and say, okay, where did we get this weird e to the ln of 2? Oh, that's 2. By definition, they're inverses, so e to the natural log of 2 is just 2. So the whole first thing is just 2 to the x. And there you go. That's the derivative of 2 to the x. And you remember that 0.69 we saw earlier? That decimal that we just said, okay, well, that's it, 0.69. That's the natural log of 2. And when we saw that 1.1 earlier, that's the natural log of 3. So here's our general rule. This one's a little harder to remember. I don't know why. The derivative of any exponential function is just the function itself times the natural log of the base. So right in the beginning when we said the derivative should be some constant times the function itself, that's the constant. It's just what it turns out to be. It's one of those things in math where it's just, well, that's what it is. If you had to memorize this rule, which you would if this were a normal calculus class, and if you take calculus 2 in a normal time, you would have to have this rule memorized. Think of it as this. The derivative of e to the x is the natural log of e times e to the x. The natural log of e just happens to be 1 by definition. Think about why that is. So that's not a different rule. That's just a nice special case of this rule. So no matter what the base is, the derivative includes the natural log of the base. It's just in the special case where the natural log of the base is 1, you don't see it. It disappears because it's just 1 times the function itself. But it's not a separate rule. It's just a special instance of this rule. 10 to the x is also a common exponential function. You'll hear that referred to as the common logarithm instead of the natural logarithm. We use it in scientific notation. We use it anytime we have to talk about really big numbers in math or really tiny numbers. So the derivative of that is just the natural log of 10 times 10 to the x, and the natural log of 10, if you just punch that into your calculator, is about 2.3. So you can see the bigger the base is, the bigger the derivative is, which should make sense because the bigger the base is, the faster it's growing. So if it's e to the x, the derivative is just the same. If it's a number bigger than e, like 3 or 4 or 10, then it's growing faster. The growth rate is growing faster than the function by this multiple of 2.3. So this is the chain rule. It's not as obvious what's what, but the outer function is exponentiation. So the outer function is 4 to the whatever. So the derivative of 4 to the whatever is the natural log of 4 times 4 to the whatever. And then you have to multiply by the derivative of the whatever. So whatever is in the exponent is the inner function, and then you just have to multiply by the derivative of that. Right? So that's the natural log of 4 times 4 to the x times secant squared of x. I just rearranged it a little bit because I don't know why. I think it looks nicer this way. It doesn't really matter. Okay, so we have 5 to the 1 over x. So the inner function here is 1 over x. The outer function here is 5 to the something. So it's the natural log of 5 times 5 to the 1 over x. So times the original thing. So there's always an exact copy of the original function in these. And then also a copy of the 1 over x. And then you have to do the derivative of 1 over x, which you would do by converting that into an exponent. So just to remember, 1 over x is x to the negative 1. Now you just use the power rule on that. The derivative of x to the negative 1 is negative x to the negative 2. And that's it. That's the answer. We could simplify that a little bit, but we don't have to. You're more than welcome just to leave it like that. I just like doing things like bringing negative signs out front. And then if you just want to call x to the negative 2 1 over x squared, the best way to write that is negative natural log of 5 times 5 to the 1 over x all over x squared. And just always remember that the natural log of 5 is just some number. Punch it into your calculator if you want to know what it is. It's 1 point something. Okay, here's a real life example. This would be an example of a function like a shock absorber. So something that does oscillate up and down like a trig function, but tamps down very quickly, right? It starts out going, and then it very quickly just like reverts back to not doing that. That's what the shock absorber does. It makes that exponential curve, or it makes that trig curve essentially stop oscillating. So you would model that by something like a trig wave, like sine of whatever, times a exponential like decay function. So that exponential decay function is what makes it have that downward motion to where it reverts back to 0. So if that's its displacement, something going up and down, but stopping at time t, then its velocity is just the derivative. So that's a kind of a complicated derivative, but it's kind of a complicated function. So here we go. We're to the point where, we should be able to bust these out pretty quickly. That's a product. So it's the first times the derivative of the second. So it's e to the negative 2t times, okay, chain rule now within the product rule. The derivative of sine is cosine. You don't mess with the 2 pi t, but then you multiply by the derivative of 2 pi t, which 2 pi is just like any other constant. The derivative of 2 pi t is just 2 pi. So that's the first part of the product rule. Then it's plus the derivative of the first, which again, the chain rule is going here. So the derivative of e to the negative 2t is e to the negative 2t times the derivative of negative 2t, which is negative 2. And then just times a copy of the second function, which is sine of 2 pi t. So, the more complicated the function in general, its derivative is going to be even more complicated. It's going to be the same kind of stuff, right? It's exponential stuff and it's trig stuff, but it's just more of it. So if this were like on an exam or a quiz, I would say just leave it like this. I want to look at the graph of the derivative. So I'm going to clean it up as much as I can. So, we're just bringing constants out front, and I just factored out the 2e to the negative 2t from both terms just because I could. If you wanted to graph this on your calculator, it helps to have it in the simplest form. So it's 2e to the negative 2t times pi times the cosine of 2 pi t minus the sine of 2 pi t. So it's still an exponential function times a trig function. It's just the trig function is more complex. It has more stuff in it. So the derivative of an exponential function times a trig function is an exponential function times a trig function. And when you look at the graph, that should make sense. So if you just think about the velocity of this thing, it starts off bouncing up and down pretty fast. So the derivative should be pretty big. So you can see, that red thing, the derivative is bouncing pretty fast between big and small, right? It's because every time it changes direction, it switches from positive velocity to negative velocity. Negative velocity means it's moving down. So those line up like we think they should. But notice the red thing is also tamping down. Right? It's also reverting back to 0. So as the thing starts to bob up and down less and less and less, it's not going as fast either. So over time, both of these things, this would be a horizontal asymptote where both of those functions were eventually going to zero. You'd see they both flatten out. Not all the way, but they so much so that it would just look like it was at y equals 0. Another application, compound interest, and in particular, if we have continuously compounded interest, that's interest that's being not compounded once a year, or once a month, or once a day, or once every second. It's literally being compounded at every moment of every second of every day. So that's what you want. This is probably the first place you saw the number E. So let's invest some money, $1,000 at 8% interest, compounded continuously, and we want to know how fast our money is growing. In other words, in that exact moment, how much money are we making? And the units for this are just going to be whatever the units for the original setup is. So at exactly 1 year, like how fast is our money growing? So that's A equals PE to the RT. You saw that in algebra class. The amount of money you have at time t is 1,000. P being your original investment, 1,000 times E, that's our buddy E, to the RT. You never use the number 8. You always use the number 0.08, right? You never really do math with percentages. So it's E to the 0.08t. So it's a number times an exponential function. Growth rate derivative, same thing. It's 1,000, so the 1,000 just is coming along for the ride, times, okay, the derivative of e to the 0.08t is e to the 0.08t times the derivative of 0.08t, which is 0.08. So just actually multiplying 1,000 times the 0.08 simplifies to that. So you're making, at any time t, you're making 80 times e to the 0.08t dollars per year, and that's going up. So you're always making a little more money. So for after 1 year, we literally just plug t equals 1. In that original formula, t is in years. That's how it works. So just 80 times e to the 0.08 times 1. Remember, e is a number, so e to the 0.08 is just some decimal. And obviously, you use your calculator, you get, it's not a very big number, $86.66 per year. So that's how much you're making after the first year at that moment. After 10 years, you would expect that you'd be making more because you have more money in the account. So the interest you're getting is based on that. And it's true, you do. It's not as much as you might think. But either way, you just plug 10 into our formula for the derivative. It's 80 times e to the 0.08 times 10, which calculator will tell you is about $178.04. So more than twice as much, but not as much as you'd think, right? But continuous interest is the best you can do as far as compound interest goes. So the only thing that really affects that is that 8%. Obviously, the bigger that number is, the bigger the derivative is going to be. So the more money we're making in this scenario.